In this lesson, we are going to look at, as it says here, a derivation for the self-inductance parameter, the constant L, for the solenoid. And we are going to derive this expression. The fact that the self-inductance parameter, which we're going to refer to as the strength of the solenoid, just like capacitance was the strength of the capacitor, is given by mu naught, script n squared, where script n squared is number of turns per unit length of the solenoid. A is the cross-sectional area of the solenoid, so A is going to be just one area loop, and we're going to multiply that by all the area loops. And script L now is the length of the solenoid, and we replace the L with a script L because the L by itself is our self-inductance parameter. So let's see how this is done. We're very quickly going to go back and remind ourselves about the B field inside the solenoid. So the current flowing through the solenoid generates flux through each current loop of the solenoid by generating the B field. And to remind you of this derivation, but as I've said, you don't want to have to do this, but why not? Let's clear off the cobwebs and go and take a look at our Amperian loop, which is our one non-circular Amperian loop. By definition, all Amperian loops are counterclockwise. So we are encompassing only the current coming out of the top of the solenoid. If we were to look at all of the current, if we made our Amperian loop capture all of the current in this diagram, we would get no net I enclosed, and this Amperian loop just gives us a result that we get B equals 0 outside of the core of the solenoid. Now inside the core of the solenoid, we're going to use our Amperian loop right here. We see that the B field inside of the solenoid, when we do Joseph law, do IDL cross R hat, we are going to get a B field in the direction to the right in this case from the current coming out of the paper. The only part of the path that will contribute to our integral, our Amperian integral, B dot ds, is the part of the path from A to B. We get cosine of 0 degrees in that case, which is 1, so we just get B times our script L. We lose the two terms here because you get cosine of 90 degrees with the B field, and as we said over here, we have B equals 0 outside the solenoid, so we lose C to D, and we then have our derivation is pretty much complete. The net I enclosed in our Amperian loop is the number of turns within the loop times the current in each loop. We divide by script L, which is now our length, so number of turns per length is our script N, and we very quickly get our B field inside the solenoid is constant. It doesn't matter whether we are in the core, very near the edge near the current, somewhere off the edge, right in the middle, or down towards the bottom. The B field is uniform constant inside the core. Well, we know that we have the empirical result, the experimental observation, that as the current in any circuit loop increases, the flux through the area defined by that loop increases linearly, and our proportionality constant was our inductance. We rearranged to solve for the inductance constant, the proportionality constant. The flux through the whole solenoid is going to be the number of turns of the solenoid times the B field in each coil times the cross-sectional area of the solenoid for each coil. That's the area that each coil encompasses. The N hat and the B field, N hat to the area and the B field give a cosine of 0 divided by I. When we plug in our result from above, the fact that the B field is mu naught script N I, so we get the B field here is our mu naught script N I. We get some very nice cancellation. We lose the I. And all I've done in this case is to multiply by the length top and bottom. So I multiplied by the length top and bottom to put it in a conventional format that you'll see in textbooks. So we have another n on L here, which is another script n. So that's why we get the n squared here. And there we have our result. The fact that the solenoid self-inductance parameter, the solenoid constant, which is the magnetic equivalent of the capacitance constant. So let's write that here so we can draw the analogy. The capacitance constant was kappa epsilon naught A over D. So a strong capacitor was strong because kappa was big, the area was big, or the separation between the plates was small. Did not depend on the charge or the voltage of the capacitor. To increase a capacitance strength, we have to physically change out the capacitor. Same thing for inductance. Inductance, this L parameter, is a strength parameter. The stronger the solenoid is, the larger all of these values. So you'll have a strong solenoid. There's going to be a lot of magnetic field strength that we're going to see when the solenoid has a large number of turns per unit length. When we physically have a large solenoid, just like when we physically had a large capacitor, a large area plate, when we physically have a large solenoid, it's big. The cross-sectional area, their big loops, is big. When it's a really long solenoid, L, you get a strong solenoid. So we are going to do a very similar comparison and type of mathematics and analysis that we did with capacitance. Hopefully that gives you some comfort that you understood what we did with capacitance, and when we do this same type of analysis with the inductor and this inductance parameter, it will make sense.